Hello everyone, so let's take a look at QP140, another Poisson process type of question where we are the owner of a pizza shop and we sell pepperoni slices at an independent constant rate of 2 per hour, and we sell cheese pizzas at an independent and constant rate of 3 per hour. This should say slices. So in part A, it's asking us what is the probability that the next order that you receive is for pepperoni, right? Now we know that this is a Poisson process because we have independent events occurring at a constant rate in both of these cases, but now we have basically two different Poisson processes. So if this is our time interval right here, let's just say we started waiting at basically a time of 0. I'm going to be selling cheese pizza at a constant rate of 3 per hour. It's a Poisson process, so we might have one come here and then maybe like this, something like so. These are all our cheese pizza arrivals. And then we also have our pepperonis going, right? So maybe I sell a pepperoni here and I sell a pepperoni here. All these events are basically independent. So because we have a Poisson process from basically everything that we've done up to this point, we know that this waiting time right here, right, between pepperonis is going to be distributed as an exponential with a rate of 2, right? 2 per hour. And then the waiting time between my cheese slices, well, that's going to be exponentially distributed as well because we have another Poisson process, but this one is occurring at a rate of 3 per hour. So these arrivals are going to be exponentially distributed with parameter 3. So to make it more formal, I'm going to define T sub P to be the waiting time until a pepperoni. We know it's distributed as an exponential with rate parameter 2, and I'll define T sub C to be basically the waiting time until a cheese, so basically exponentially distributed with parameter 3. So it's asking us basically what is the probability that the next order we receive is for pepperoni. So the probability that T sub P is less than T sub C. Now this is just the same thing as basically we're trying to find the probability that the minimum between basically T sub P and T sub C is equal to T sub P. So just the probability that the smallest arrival time between these two right here happens to be the one for pepperoni. So this right here is just an order statistic, and we basically have a good understanding of order statistics at this point. So we can basically think about this probability here, right? The probability that the minimum between T sub P and T sub C is equal to T sub P as basically, let's just take every single possible value that T sub P could take. So our first pepperoni could arrive here, or here, or here, or here in infinitely many places, because this is a continuous distribution after all. And then for each of these, let's just say I fixed one for now, right? This is just going to be T sub P. Let's say it was right here. What is the probability that this was actually the minimum at this point right here? Well, basically it's the probability that T sub C comes after, right? So to do that, I'm going to integrate over all the possible values that T sub P could take, again, because we have a continuous distribution here, right? So what values can T sub P take? Well, it starts at 0 when our time is equal to 0, and we can go all the way up to infinity, right? And we're basically summing up all the possible values that T sub P could take. So basically, we're just summing up the density function for f of T sub P, I'll call it, of, well, what's our variable here? Let's just call it x. And then for every single one of these points, we need to find the probability that T sub C comes after that point, right? So given a specific value, let's say that this one came at time x, what's the probability that our first cheese comes after that? Well, that's just going to be equal to 1 minus the CDF of T sub C. So I'll call that f of T sub C with a capital F of x, where x is basically this value right here that we fixed. So we're integrating with respect to x, right? X is all the possible values in our time interval. Okay, so now what is the density function first of T sub P of x? Well, it's just going to basically be, well, it's exponentially distributed with rate parameter 2. So we have 2 times e to the power of negative 2 times x. Well, now what is 1 minus basically the CDF of T sub C of x? If you remember back in QP111 when we derived the exponential distribution, basically we derived it from a Poisson, so we can relate this to a Poisson, right? Asking what is the probability that our first event comes after this point x right here is just like asking what is the probability that 0 events occur before x. And that's exactly what this term is right here. That's because f sub T C of x, well, that's just defined as the CDF, so it's just the probability that T sub C is less than or equal to x, which is just the same thing as 1 minus the probability that T sub C is greater than x, right? So this right here is just saying, like, basically what is the probability that T sub C is greater than this value x. And again, like we talked about earlier, you can relate that to the Poisson by just calculating the probability that 0 events come within this time window between 0 and x. That's the probability that our first slice comes after x, the probability that 0 come before. And because we have a Poisson with rate parameter 3, the probability that a Poisson is equal to 0, if we plug into the PDF of the Poisson, is just going to be e to the power of negative 3 in this case, because that is our rate parameter, times x. So now we can use these things in our equation right here. We're just going to be taking the integral from 0 to infinity of when we plug in this, it's going to be 2e to the power of negative 2x. And then in here, we're going to have 1 minus, actually, no, sorry, this was equal to that. So we just have e to the power of negative 3x dx. So again, this right here is just going to be the probability that t sub p takes certain values of x, and we're summing up over all those possible values of x, where x represents our time, and we're multiplying that by the probability that it is the first one. So the probability that the first cheese comes after this point x. So now we can just integrate this. We can combine terms in here. So let's do so over here. This is going to be equal to the integral from 0 to infinity of 2 times e to the power of basically negative 2x plus negative 3x, so negative 5x dx. This integral, when evaluated, is just going to be 2 times e to the power of negative 5x divided by 5. Then whoops, don't forget about the negative sign like I did, because we're differentiating this term right here, which has a negative 5 out front, so we have to pull that down, and we're going to evaluate this whole thing right here from infinity to 0. Now obviously as x goes to infinity, this term right here is going to go to 0, so this whole first term is going to go to 0, so this is going to be equal to 0 minus, and then when we plug in 0 right here, we're going to have basically negative, this is going to be a 1 right here, and then we're going to have 2/5, so negative 2/5, also known as 2/5. So 2/5 is the probability that our next order that we receive is pepperoni, so that is the answer for part A, where you can see we derived basically the whole thing over here. It's basically an order statistic. Also in general, what you can basically show is if we have two different Poisson processes happening, maybe with different exponential rate parameters, right? Well, then all we have to do is basically just change out the values that we had in here, and you'll get basically lambda A divided by lambda A plus lambda B in general. So this would be the probability that an event from our Poisson process A happened before an event from our Poisson process B, where these are the rate parameters from those processes, right? And this right here is a very useful thing to know, right? You don't want to do all these integrals every time. You can just know this. And this also intuitively just makes a lot of sense. If I expect 2 pepperonis to come every hour and 3 cheese to come every hour, then I basically expect 5 general slices to come every hour, and 2 out of those are probably going to be pepperoni. So this makes a lot of sense. Okay, so now part B and part C should be absolute gimmies, especially after all the Poisson and gamma distribution stuff that we've done. So let's look at part B first, asking what is the expected waiting time until you sell your 4th slice? So again, we have a Poisson process here. We're selling cheese and pepperoni pizza. So maybe I get some cheeses at these times right here, and maybe I get some pepperonis like this. So what's the expected waiting time until I sell my 4th slice? Well, my pepperonis are coming in at a rate of 2 per hour, and my cheeses are coming in at a rate of 3 per hour, first of all. So in general, don't overthink it. We have independent events occurring at a constant rate, so the number of slices that we expect to come per hour are just going to be 2 per hour plus 3 per hour, so 5 slices in general per hour. So let's call this here lambda. So now what's the expected waiting time until we sell our 4th slice? So all I've done, you can see that you can pretty simply just combine these Poisson processes into one right here. So now we just need to find basically the expected waiting time until my 4th slice in a Poisson process with parameter 5. Now, how is the 4th arrival in a Poisson process distributed? Well, we've already derived it. It's the gamma distribution. Now, what's the expected value of a gamma distribution? Well, we also derived that in QP number 137, so that's just going to be equal to basically n divided by lambda, where lambda is our rate parameter, and n is basically the arrival that we're waiting for. So in our case, we're basically just waiting for our 4th arrival, and we have a rate parameter of 5. So the expected waiting time until my 4th slice, since lambda is in terms of hours, is basically going to be 4/5 of an hour. That also just makes perfect sense because if events are occurring at a rate of 5 per hour and they're occurring at a constant rate, which they are, well then we know that basically they're going to be in general occurring once every 12 minutes. All we did to get that was just by taking 5 per hour and just dividing both sides by 5 on top and on bottom. And when we did that, that's just going to give us 1 per 12 minutes, obviously. Then obviously the time between our arrivals are going to be exponentially distributed. We know the expected value of an exponential, again from QP 137, it's just going to be 1 divided by our rate parameter, so 12 minutes. And then we're summing up 4 of these exponentials, right, to get our 4th slice. So we're summing up 4 times 12 minutes. That's going to be our expected value. So the expected waiting time until our 4th slice is just going to be the expected waiting time for 4 different exponentials. So we're just summing up 12 4 different times. And wouldn't you know it, 4 times 12 is equal to 48, which is exactly 4/5 of an hour, right? So the answer is 4/5 of an hour, or 48 minutes. So now let's go on to part C, which should be even easier, right? Given that we sold 8 consecutive slices, what is the probability that at least one of them was a cheese slice? And we know that that's just the same thing as taking 1 minus the probability of no cheese slices, right? So all pepperoni. So in my Poisson process, I'd have to get every single one to be a pepperoni. And now don't overthink this. In part A, we found that the probability at any one of these points of getting a pepperoni was just equal to 2/5. So because we know from part A that the probability of us getting our first slice as a pepperoni was equal to 2/5, and we know the exponential distribution is memoryless, again from QP 137. So we know exactly at this point right here, when we get our first pepperoni, it's basically going to reset. Meaning that from this point right here, where we get our pepperoni with probability 2/5, the probability that the next one after that is going to be pepperoni is going to be exactly the same. It's also going to be 2/5, and same with all the arrivals afterwards. So all of these are completely independent. What do we have here? Well, we just have a binomial. The probability of no cheese is going to be the probability that all 8 are pepperoni. So what is that? They're all independent. It's just going to be 2/5 8 different times, so 2/5 to the power of 8. So the probability of at least one cheese is going to be 1 minus 2/5 to the power of 8. So just a super simple binomial question right here.